Good morning, everybody. All right, so today I want to talk about two quick, simple topics, kind of notational thing for you guys. And the first one has to do with what we call a recursive sequence. So, a recursive sequence is when we define our terms based on previous terms. So, we might do an example of a recursive sequence as, let's say, a sub n, our general term, is equal to a sub n minus 1, let's say minus 3. Oftentimes, along with this general term, we have to know where our sequence is going to start. So we're going to say that a sub 1 is equal to 10. All right? Now, if I want to write out the first few terms of this so you can get an idea of what this recursive sequence would be, of course, the first term would end up being 10. Now, the second term says take the term before it and subtract 3. So to get the second term, I'm going to take the first term and I'm going to subtract 3 from it, 7. And then to get the third term, so we would say a sub 3 is going to be equal to a sub 2 minus 3. So that's a sub 2, of course, is that 7. Subtract 3, we get 4. And then the next term will be 1, and then negative 2, and then negative 5, and so on. Okay, and this is another infinite sequence, right? That is defined, recursively based on previous terms. The unfortunate thing about having a recursive sequence like this is if you want the 100th term, that means you have to know the 99th term, and the 98th term, and the 97th term, and so on. And so things can get a little bit dicey when you're trying to go out that many terms, all right? It's nicer to really have kind of a general formula, okay, for your terms. Also, as an example, sometimes instead of saying a sub 1 or a sub n is equal to a sub n minus 1, and some kind of action on there, we could say that a sub n plus 1 is equal to a sub n minus 3. This is really the same sequence of above. It says in order to get the next term, take the term that you're at and subtract 3. I mean, this is the same sequence. Just defined your a sub n plus 1 based on the previous term, okay? A really famous recursive sequence that you're going to write out a couple terms for in the web work homework tonight is the Fibonacci sequence. Fibonacci sequence, we define the first two terms are both going to be equal to 1, and then from there on out, the next term is going to be the sum of the two previous. Right? So the third term is going to be the sum of a sub 1 and a sub 2. The fourth term is going to be the sum of a sub 3 and a sub 2, and so on, right? The fourth term is the second term plus the third term, and so on, okay? Also, I wanted to talk a little bit about a bracket notation, which is going to come up, and you'll see it sometimes, that we can define a sequence looking like such. So this is an infinite sequence here, where really our general term comes from the expression inside the bracket. So that would be a sub n is equal to n minus 1 factorial all over n plus 1 factorial. I hope you guys remember what factorials are. This general term, by the way, because it's a factorial divided by a factorial, a whole bunch of things are going to cancel out, right? I mean, we can take this particular n sub, or a sub n, and the numerator is really n minus 1 times n minus 2 times n minus 3 all the way down to 3 times 2 times 1, right? If you remember, 7 factorial is 7 times 6 times 5 times 4 times 3 times 2 times 1, and so on. And then the denominator here is n plus 1 times n times n minus 1 times n minus 2 times n minus 3, all the way down again to 3 times 2 times 1. Obviously, a lot of stuff is going to cancel out here. The n minus 1 over n minus 1 and the n minus 2s and the 3, 2, 1, and all the middle terms are going to end up canceling out. And so this general term really could just be written as n plus 1 times n, all right? In which case, the first few terms, if we write out the first few terms of the sequence, the first term, we plug in 1, you're going to get 1/2. Plug in 2, you're going to get 3 times 2, or 1/6. Plug in 3, you're going to get 4 times 3, which is 1/12. Plug in 4, you're going to get 5 times 4, which is 1 over 20. And so, yeah, right? It's almost even nicer to write it out as 1 over 2 times 1, 1 over 2 times 3, 1 over 3 times 4, 1 over 4 times 5, and of course that's just going to continue on, okay? So that is two different types of notations that we're going to have for sequences that you're going to see, okay? The next thing I'd like to talk about today that you're going to see is limits of a sequence, right? Taking the limit. Well, since a function and a sequence kind of go hand in hand, except of course their domains. The sequence, you just have a domain of integers, whereas a function, most of the time your domain is a subset of the real numbers, okay? But here we're going to have to be able to take limits, and we're going to do so a lot like taking the limit of a function. So if I give you a sequence defined here as 2n over n plus 1, n starts at 1, goes off to infinity, right? This sequence, its general term is 2n over n plus 1. Nice, this is not recursive, okay? We're not really going to be taking limits of recursive sequences or converting a lot of recursive sequences into explicit, right? This would be more of an explicit formula for our sequence. But we will say, look, this sequence here is a lot like the function f of x equals 2x over x plus 1, right? And this function, we know the limit as x goes to infinity of this function, 2x over x plus 1. We know that's going to, tend towards 2. Well, the sequence is really going to head towards the same thing. Just because you're plugging in integers instead of real numbers doesn't mean that as those integers, shoot out to infinity, you're still going to be heading towards the same value of 2, right? If the function has a limit, the sequence as well is going to tend towards that same limit and that same value. Now, look, when a sequence has a limit, when that limit exists, and it's a finite number, right? If that limit goes to a particular value like this, we would say that a sub n converges to 2, right? Much like the function tends towards 2, the sequence is also going to converge towards 2. Now, if, of course, the limit does not exist, or the limit is infinite, we would say that the sequence diverges. All right, it doesn't converge to an actual number. We would say the limit diverges. Okay, just another quick example. Right, let's say our sequence is defined by the general term sine of n over n squared. Okay, just like functions, we can kind of bound and squeeze this sequence, you know, and what I mean by squeezing it, I mean like kind of sandwiching it between two things, right? So we know sine of n is going to always stay in between positive and negative 1. Right? I mean, it's always, it bounces back and forth. It doesn't matter that n is an integer. Sine is never going to be, bigger than 1. It's never going to be smaller than negative 1, right? So then as long as n is a positive number, which it is, we're only plugging in our positive integers like first 1, 2, and 3, and so on, then we can divide by n squared and show that sine of n over n squared has got to be in between 1 over n squared and negative 1 over n squared, right? So we've got sine of n over n squared kind of sandwiched in between these two other functions or sequences. They're sandwiched in between, and the limit of these two sequences, I know the limit as n goes to infinity of negative 1 over n squared is going to be the same limit as n goes to infinity of positive 1 over n squared. I know both of these things tend towards 0. Okay? Therefore, the limit as n goes to infinity of sine of n over n squared is also going to have to go to 0. This is by what's called the squeeze theorem, or you can say the sandwich principle, right? We're just saying that's heading off to 0, that's heading off to 0, so this is being squeezed in between those functions, and that must also end up going to 0, okay? There endeth the lesson for today, and I'll be online later on for you guys. So stop by if you have any questions, and we will pick up some more of this stuff tomorrow. Please check out the web work, 5 questions, see what you can get done, all right? Thanks, guys.